Okay, so last time we talked symmetric matrix. Symmetric matrix has nice properties. For instance, this theorem, all eigenvalues of a real symmetric matrix, are real. So there's no complex, complex eigenvalues. And we proved this thing by using inner product. Okay, inner product. So we evaluated this inner product in two distinct ways, and then we find this equation. Then where this eigenvector v is non-zero, okay, non-zero eigenvector. Then we can just divide. So we get the eigenvalue lambda equals its complex conjugate. Then we finally find this eigenvalue lambda is real. Okay, is real. Is real. Okay, the next theorem is eigenvectors of symmetric matrix are orthogonal. Okay, orthogonal. This is important. We already know that eigenvalue for matrix, square matrix, if it has distinct eigenvalues, then the eigenvectors correspond to distinct eigenvalues. They are linearly independent. Okay, they are linearly independent. So this try to spine as large as, the space as large as possible, spanned by the eigenvectors. And for symmetric matrix, we can even have a stronger property. They are not just linearly independent. They are actually orthogonal. The idea that is we can define inner product, okay, inner product between two vectors, and we can evaluate this inner product in distinct ways, okay, in two ways, and we find, okay, in this, so we get an equation, lambda 1 multiple of this inner product v1 v2 equals lambda 2 of this dot of this inner product. So here lambda 1, lambda 2, they are distinct eigenvalues. So if you move terms, so you get lambda 1 subtract lambda 2 times the inner product v2 with v1. You find this to be 0. So here lambda 1 minus lambda 2 is not a zero, non-zero, because the two eigenvalues are distinct. So we finally get the dot product. Okay, the dot product should be 0, which means v1 is orthogonal to v2. Okay, so we are done. Okay. Okay, now suppose we continue. Let's assume that S is symmetric matrix. Okay, now suppose we continue assume that S is symmetric. Okay, now suppose S is a symmetric matrix. So suppose we continue assume that. Suppose that S is a symmetric matrix. Let's see, n by n matrix. So we know S equals ST. Now, if so, the characteristic polynomial of this n by n matrix is degree n. Okay, degree n. Then it has most n distinct eigenvalues. Okay, so if S has distinct n eigenvalues, n distinct eigenvalues. Let's see, lambda 1, lambda 2, lambda n. Okay, so they are all pairwise distinct. Then we know with the corresponding eigenvectors. Then the eigenvectors should be linearly, we already know they are linearly independent. However, we know a stronger property, actually they are orthogonal. They are orthogonal, okay? Of course, so this is stronger than just being linearly independent, stronger than being linearly independent. So for general matrix, distinct eigenvectors correspond to distinct eigenvalues, linearly independent. So here we know it's orthogonal. So we know actually the span of this eigenvectors v1, v2, blah blah blah, v1, v2, da da da, vn. This span actually Rn. Okay, this span Rn. Okay. Okay. Now you may ask, what happens if there are certain multiplicities? Okay. What happens if some eigenvalues that they coincide? They coincide. Fact is, even if there are certain eigenvalues coincide, so this fact is not easy to prove. V1, V2, Vn. Span this is equal to Rn, even if some eigenvalues coincide. Some eigenvalues are the same. Okay, so you often see this word, degeneracy case, i.e. certain eigenvalues reduced to one eigenvalue. Okay, so this fact, we will not prove this fact. It's out of scope of this course. We will not prove this. Okay, so we know that now we know the eigenvectors span the whole space. Okay, span the whole space for symmetric matrix. So this property for general matrix is not satisfied. Okay, it's possible that if you have certain matrix non-symmetric, that the eigenvalues, the eigenvectors does not span the total space. Okay. Okay. Now remember what S does is if we plug in V1, so we may view S as a projection matrix. So what S does is, so V1, we use S, then we get SV1, then what we get is lambda 1 V1. Okay, V2 is lambda 2 V2. Okay, Vn apply S, then we get SVn, which is lambda n Vn. Okay, lambda n Vn. So this is, you know, the V1, V2, Vn, they are orthogonal. So here we can view S as a projection matrix. Okay, that the direction that it projects is on its eigenvectors. Okay, we may view the matrix S as a projection matrix. Okay, so for the vector, its vector, then what is this for this eigenvector V1, V2, Vn? So S does is project on this vector V, okay, and reskew it by the eigenvector. Okay, for each direction, just S reskew. Okay, reskew. Now, reskew. Okay. Okay. Now for each dimension, for each V1, V2, okay, for each orthogonal direction, then we can, if we choose V1 to be unit vector, if we choose V1, V2 eigenvectors to be unit vectors, if we normalize, okay, i.e. normalize its eigenvectors, normalize its Vi, i.e. make them to be unit vector, then the projection onto V1 is P, which is V1 times V1 transpose. Okay, V1 times V1 transpose. Remember, it's not just projection. Okay, you see, when V1 project on the direction V1, but we also reskew by the factor lambda 1. Okay, reskew by lambda 1. So what this matrix does for V1 is multiply lambda 1. Okay, we also need to reskew this factor lambda 1. Okay, so this is P1. So this tells what this matrix S does on V1. Okay, now if you you see, then you see P1, what P1 V1, this will get P1 V1 times V1 transpose V1. Okay, so V1 transpose, so V1 transpose with times V1, this we get actually V1 with dot product itself. Okay, so if you write V1 as x1 x x2 xn, you see V1 transpose will be x1 x2 xn. Okay, so V1 transpose times V1, so row vector times column vector, then we get actually, this is actually dot product. Then what we get is x squared plus x2 squared, component wise multiply xn squared. Because we already normalized the V1 unit vector, so this is actually the norm of this V1. So this is actually y. Okay, this is y. Okay, so this is actually, you see this dot product or the bracket V1 with V1 is y. So this is actually y, lambda y V1 times 1. So this is actually lambda y V1. I.e., this P, what this P does is we plug in V1, output lambda 1 V1. Okay, lambda 1 V1. Moreover, if you plug in any orthogonal direction, for instance, any other orthogonal direction, for instance, V2. So you see P1 V2, what happened if we plug in V2? Now you see lambda 1 V1 transpose V2. Now remember, the eigenvectors are orthogonal corresponding to distinct eigenvalues. They are orthogonal. So it's lambda 1 V1 dot product with V2. V1 dot product with V2, inner product. This actually tells us, V1, this is 0 because they are orthogonal. V1 is orthogonal to V2. Okay, so this we get a 0. Okay, you see, if you plug in the direction V2, we actually get a 0 vector. Okay, 0 vector. So this P1 is indeed the projection onto the V1 direction, etc. You can also check P1 V3, P1 V4, etc., and P1 Vn. All these matrices. So this is indeed projection onto the V1 direction. Okay, P1, and also reskew by the factor lambda 1. Okay, so similarly we define P2 projection onto V2 direction, V2 transpose, and also reskew by the factor lambda 2. Okay, by this factor lambda 2. You can also check P2. So this is a projection on V2 direction and also reskew by lambda 2. So you can check P2 V1, you get a 0. Okay, easily check. P2 V2 is lambda 2 V2. Okay, if you work out, so V2 transpose times V2. Now this actually gives us lambda 2 V2 and V2 inner product with V2. V2 inner product with itself or dot product with itself. This we get 1. Okay, because we already choose eigenvectors to be unit vector. Okay, unit vector. This is lambda 2 V2. Okay, so etc. So we can add this projection all together. We can add all this projection together. So if we let if we sum this thing, P1 I from 1 to n, okay, So we define P1, P2, etc., etc. We can define Pn as lambda n, Vn, Vn transpose. Okay. Now you see, if we add this projection matrix together, okay, projection matrix together. So this will be lambda 1 V1, V1 transpose plus lambda 2 V2, V2 transpose, etc., etc., plus lambda n, Vn, Vn transpose. Now you check this. Let's, for instance, let's this be P, defined to be the thing. Now you see P on lambda 1, P V1 is lambda 1 V1. P on V2 is lambda 2 V2, etc., etc. P Vn is lambda n Vn. Now remember what S does is S V1 equals lambda 1 V1. Okay, S V2 equals lambda 2 V2. Blah, 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 blah. S Vn equals lambda n Vn. So you see what this matrix P does and what this S does to these eigenvectors. They are the same. Okay, they are the same. So we can conclude. So the action of P, the action is the action of P and S are the same. On this V1, V2, Vn. Now remember V1, V2, Vn, they span the total space Rn. Okay, they span the total space Rn. So this actually tells us the P and S, they should be exactly same as matrix. Okay, so we can conclude since this is the everything V1, V2, Vn. Spine is everything. Okay, spine is Rn. So this tells us that what this P and S does is on Rn is the same. So this tells us that S equals P equals lambda 1 V1 V1 transpose plus blah 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 plus lambda n Vn transpose. This is the famous spectral decomposition. So this is famous. Okay, the famous spectral decomposition. Decomposition of a symmetric matrix. Okay. Now you need to be careful. If we have a general matrix, we can write down its eigenvalue, blah blah blah. Now, if you do this manner, you will have trouble. Okay. So for general matrix, we cannot we may fail to write down in this form. Okay, it's special property that works for symmetric matrix. Okay, it's a spectral decomposition. Okay. Now then here symmetric matrix, we can always diagonalize it. They are diagonalizable. So let's next talk about the diagonalization of symmetric matrix. Then we will give some example. Okay, so remember the diagonalization of a matrix. We put eigenvalues, okay? Put eigenvalues on the main diagonal. So let gamma be the diagonal matrix with the eigenvalues on the main diagonal terms. Lambda 1, lambda 2, lambda n. Okay, if you write a matrix form, so this will be lambda 1, lambda 2 on the main diagonal, lambda n. Okay, on the main diagonal. Everything others are 0. Okay, so remember, we need the matrix X. We write matrix X as column vectors is given by the eigenvectors. Okay, eigenvectors. So what this matrix X does is we change the base. Okay, we change the base. Remember, X does it change the base. E1 goes to V1. Remember, E1 is 1. The first entry is 1. The first component is 1. Then a bunch of other zeros. Now E2 goes to V2. Okay. En goes to Vn. Okay. So remember, so if we change X, we apply X, then we E1 transpose to V. Okay, E transpose to V. Okay, and then we apply the matrix X. Then this V1 goes to lambda V1. So if you apply S again here, then you get lambda 1 V1. Okay, lambda 1 V1. And then V2 you apply S, you get lambda 2 V2. Ratio, okay, S lambda N Vn. Okay, now we change V back to E. Okay, we change V back to E. Okay, change V back to E. Okay, what happened? Okay. Yeah, my note goes wrong somehow. Okay. What happened? Do I need to start a new notebook? Maybe I start a new book. This notebook just goes wrong. Let's try a new one. Let's try a new one. Okay, I think it works now. Okay. Okay, it works. Okay, now we change back. Okay, sorry. Now once we get a V1, we change back to E1. Okay. Now remember, X change E1 to V1. Okay. Now X inverse. We do the inverse. X inverse. This will change V1 to E1. So this will lambda 1 V1, we get a lambda 1 E1. Okay. So change back to, so lambda 2 V2 will becomes lambda 2 E2. This do the X inverse. So this we get lambda N En. Okay. You see what we finally get is we apply X. Okay. We apply S and then we apply X inverse. Okay. So the letter on the right do the action first. Okay. And then the letter on the left do the last, do the action last. So this actually tells us this E1 goes to lambda 1 E1. E2 goes to lambda 2 E2. En goes to lambda N En. So this actually is what a diagonal matrix does. Okay, this is exactly what the diagonal matrix does. So we can get lambda X inverse S X is actually the diagonal matrix gamma. Okay, and then we solve for S. We solve for S. S is you multiply X on the left. Okay, you multiply X left, You multiply x on the right. You multiply x inverse on the right. So you get x inverse on the right. So this you get s equal to x gamma x inverse. Okay, x gamma x inverse. Okay. Okay. Now we do another thing. So here we have some special property. So if we check this form for symmetric matrix, it's special. Okay, so we have this. X is v1, v2, vn, column vector. Now x transpose. Let's see what x transpose is. X transpose. We write column vectors as root vectors. Okay, so x transpose will be v1. Now we write as root vectors. v2, vn. Okay, vn. Now we check x transpose times x. Okay, so it's root vector times column vector. Okay, root vector times column vector. root n times v1, v2, vn. Now, if you do this matrix multiplication, you see what is ij in G. X transpose times x. It's a matrix. We find the ij in G. The ij in G of the product is the ith column times the G's rule. Okay, the ith column. You see what is the ith column? 1, 2. So x transpose ith column. 1, 2. Ith column is actually, you see, it's a vi, the vector vi. Okay. Now the G column of x is actually vg. Okay, vg. Now the dot product, root vector times column vector. Okay, this is we have this. This is 1 if I equal to j. Okay, so vi times vi, dot product is 1 because it's unit vector. Okay, it is 0 if I not equal to j. This is because then vi, vj correspond to distinct eigenvalues. Okay, eigenvectors correspond to distinct eigenvalues. They are orthogonal, so their dot product are 0. So we have a notation which is called the Kronecker third. Okay, the Kronecker third. Okay, Kronecker third is defined as it is 1 if I equal to g, 0 if I not equal to g. Kronecker third notation. Kronecker third notation. Okay, you see what happened is, so if I not equal to j, this is 0. So the off diagonal inches, okay, is 0. All of the diagonal inches are 0, and the diagonal inches are equal to j. Then you get 1. So we get x transpose times x is actually diagonal entry is 1, blah 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 1. Okay, then all other entries are 0. So this is actually the identity matrix. So this tells us x inverse, x transpose is actually equal to x inverse. Okay, because if you check x transpose times x is I, okay, x inverse times x is also I. So x transpose correspond to x inverse. Okay, if we diagonalize a symmetric matrix, then we have S equals x gamma x inverse. So actually, then we can actually get x gamma x inverse is x transpose. Okay, transpose. So two matrices, they are called congruent. We give a definition. Two matrix A is called two matrix A and B. two matrices A and B are congruent. If A equal to X, B, X transpose for some invertible matrix. Invertible or for some invertible matrix X. Okay. This actually definition. Okay, let's see some example. Let's see some example. How do we write a symmetric matrix as projection matrices? Okay, let's see some example. See S to be this. S to be -2, 6, 6, 7. Now, first of all, symmetric. Okay, symmetric. Now we find the characteristic polynomial. Find eigenvalues and eigenvectors. Okay, so find characteristic polynomial. So S minus lambda I, take determinant. So this will be -2 minus lambda, 7 minus lambda. All diagonal terms are fixed. Okay, let's find it. Now 2 by 2 is easy. 2 by 2 is easy. So this is -2 minus lambda times AD minus BC. So this 7 minus lambda, subtract 6 times 6. So if you do the algebra, so this will be lambda squared. So the coefficient of the lambda term is -7 plus 2. So it's -5 lambda. And then you do the constant term, -15, -36. It's -14, -36. You get a -50. Okay, we can factor this. -10 plus 5 quadratic. Okay, so we have, you see, the characteristic polynomial has two roots. Okay, two roots. So the one of the root is lambda equals 10. Another root is lambda equals -5. Comes from the two factors. Okay, so it's 2 by 2 matrix, has two distinct eigenvalues. So this matrix is diagonalizable. Okay, let's do the first eigenvalue and the eigenvector. So we do the first eigenvalue. So lambda equals 10. Let's do lambda equals 10. So we need S times V equals 10 of V. So let's suppose V to be xy. Then the equation, remember S is -2766. So it's times xy. This will be the first rule will be -6x, -2x plus 6y, and this is a 10xy. This will be 6x plus 7y. This will be. Now you can use just one of the equation. Okay, so you use the first component. You get -2x plus 6y is 10x. So we get 6y is 12x. Okay, so y is 2x. Okay, so we get this equation, y is 2x. Or you use the second equation. We should get the same answer. Okay, 6x plus 7y is 10 of y. Okay, so we get move terms. So we get a 6x is 10y minus 7y, which is 3y. So if you divide by 3, so we get a y is 2x again. So you see y is 2x, y is 2x are the same. So you can either use either equation. Okay, so we get y of eigenvector should be x, y should be y is 2x. Remember, x is x, y is 2x. So if you factor out x, you get a x multiple of 1, 2. Okay. Okay. So then we get an eigenvector C 1 2. Okay, let's just do the 1 2. Now we need to normalize it. Okay, normalize it. Normalized eigenvector. Okay, so let's see, we choose v1 to be 1 over root of 5. Root of 5 comes from, we divide it, so divided by the norm of this thing. Okay, 1 2. The vector 1 2 has norm square root of 5. So you divide by its square by its norm. So you get a unit vector. Okay, so v1 is a unit vector. So this is the 1 over root 5, 2 over root 5 unit vector. Now let's similarly find v2. Find v2. So v2, so we need a lambda 2 is negative 5, remember. So the s negative 2, 6, 6, 7 times xy is, we need a eigenvalue 5, negative 5, xy. Okay, now what do we get? Root times column. So we get negative 2x plus 6y. We get this is negative 5x. 6x plus 7y, we get negative 5y. Okay, you can use either equation. So the first equation, let's see, we get, so move 2x to the other side. So you get a 6y is negative 5x plus 2x, which is negative 3x. So x is equal to negative 2y. Okay, you can also get a similar result. So if you use 2, then we get a 6x equals negative 5x minus negative 5y minus 7y. So negative 12y. So we get divided by 6. So we get a x is divided by 6. Negative 12y divided by 6. We get negative 2y. So once again, we get x equals negative 2y. Or negative 2y equals x. So you see the results that we get are the same. You see, use this result, use either equation. So we get the same. We get the same, okay, result. Same relation between x and y. Then we can choose eigenvector as, okay, let's choose some eigenvector. Okay, so the eigenvector that we choose should be, what should be? So the eigenvector should be xy. Now x is negative 2y, so it's negative 2y, y. So if you factor out y, this will be y, negative 2, 1. So we can choose v2, normalize this. So it's a factor times root 2, it's a factor times negative 2, 1. So we can choose v2. Choose v2 to be, its norm is root 5 again. Negative 2, 1. Okay, why do we see we choose? Why do we see we choose? Because indeed we should choose. Remember, eigenvector is only determined. We can only determine its direction. Okay, direction. So you can, even if you normalize it, you can also flip the direction. So you can choose 1 over root 5 or negative 1 over root 5. Multiply this negative 2y. Okay, so we get a opposite direction. So somehow we need to actually to choose one of the direction. Okay, one of the direction. So now what is this matrix X? What is the matrix X? Remember, matrix X we write as column vectors of this unit eigenvectors. Okay, unit eigenvectors. So X will be v1. You see, v1 is 1 over root 5, 2 over root 5. Okay, then v2. What is v2? v2 is negative 2 over root 5, 1 over root 5. Okay, so if you can write as 1 over root 5, 1 negative 2 2. Okay, so let's see determinant of what determinant of x is. Determinant of x is, you see, we have a scalar multiple of some integer matrix, integral matrix. So scalar multiple, so actually we get 1 over root 5 to the power 2. Use the property of determinant. So the dimension is 2 by 2. So the scalar actually should multiply to the power 2. Okay. Okay, and then determinant of this matrix 1, 1, negative 2, 2. Okay. So this determinant, so this is 1 over root 5 squared is we get a 1 over 5. Now this determinant we get a 1 times 1 minus negative 2 times 2. So this is, okay, so this is 1 over 5 times y minus negative 4. So it's 1 plus 4. So this is 1 over 5 times 5. So we get 1. Okay. So you see, no surprise that the X matrix has determinant 1. Okay, determinant 1. Okay, so it's not a surprise. So this matrix X, if you write for symmetric matrix, if you write its eigenvectors in this manner, unit eigenvectors in this manner as well as column vectors, then the determinant should be plus minus 1. Okay. So if you change the direction of the one of the eigenvectors, okay, for instance, if you multiply a column by 1, by negative 1, then actually we get this determinant should be negative 1. Okay, you either get a 1 or negative 1. Okay, now we don't need to find X inverse. Now it's not difficult to find X inverse from this problem. It's really easy. Now we just do X transpose. Okay, you do X transpose, we get X inverse. Okay, X transpose is, you see, X transpose, we just flip the off diagonal entries 1 and 1. So 2 becomes negative 2, negative 2 becomes 2. Okay, you flip with respect to the main diagonal. Okay, you can check. Okay, you can check. Indeed, we get so S will be, this matrix S will be X gamma X transpose. Okay, so this gamma is the first, don't mix up the order. Okay, the order of these eigenvectors. Okay, because we write V1 first, so the diagonal thing should be lambda 1. Remember lambda 1 by our choice, lambda 1 is 10. Lambda 1 is 10. Lambda 2 is negative 5. Okay. Now if you change the position of this lambda 1, lambda 2, okay, if you name lambda 1 to be lambda 2, lambda 2 to be lambda 1, then you should flip the corresponding position for the eigenvectors. Okay. Okay, so this you can check. So X is 1 over root 5. So this is a y negative 2, 2, 1. This gamma is 10 negative 5. And X transpose is 1 over root 5, y 1 negative 2, 2. Check this. So 1 over root 5 times 1 over root 5, then we get 1 over 5. Okay, 1 over 5. And then what do we get for the first product of the matrix? Okay, first root times first column. First root times first column. 1 times 10. Negative 2 times 0. So we get a 10 here. First root times second column. First root 1 times 0. Negative 2 times negative 5. So we get a 10 here. Okay, second root times first column. Second root times first column. 2 times 10 plus 1 times 0. So we get a 20. Okay. Second root times second column. So we get this. Okay, so we get this. Times 1, 2, negative 2, 1. Okay. Now we just divide 5. Divided by 5. Then what do we get? 10 divided by 5. So we get a 2, 2, 4, negative 1 times 1, 1, negative 2, 2. Okay, now the first root times the first column. Okay, Okay. First row times first column. So the first row times first column. So we get 2 times 1 plus 2 times -2. Okay, first row times first column. First row times second column. So it's 2 times 2 plus 2 times 1. Second row times first column, 4 times 1 plus -1 times -2. Second row times second column, 4 times 2 plus -1 times 1. Okay, if work this out. So the y1 entry will be 2 minus 4, so we get a -2. The second entry will be 4 plus 2, 6. This will be 6 plus 2, 4 plus 2, so we get a 6. Now this will get 8 minus 1, 7. So this is exactly S. Okay, if you check, this is indeed our initial matrix X. Okay, so remember what our matrix X is given. You see, this matrix X is 2, 6, 6, 7. Okay, so this works. Okay, this example works. Okay. More example maybe. More example. Okay, let's see this example. Let S be this. Okay, let S be this matrix. 3, 1, 1, 3. So you see this symmetric. So let's see. So first find characteristic polynomial. So you find S minus lambda I. So this is 3, 3, 1, 1 minus lambda. So you get a 3 minus lambda, 3 minus lambda. The off diagonal entries does not change. So if you take determinant, then we get a determinant of this thing. Let's just the determinant, we just use this notation. Okay, so this gives us determinant. And then this gives us 3 minus lambda times 3 minus lambda. So it's 3 minus lambda squared minus 1 times 1. Okay, now this can easily factored because it's difference of two perfect squares. So it's 3 minus lambda minus 1 times 3 minus lambda plus 1. So we get this is 2 minus lambda, 4 minus lambda. So we have 2 eigenvalues. Okay, so this is the characteristic polynomial. The root of the characteristic polynomial tells us the eigenvalues. Okay, so we have 2 eigenvalues. So lambda 1 is 2, lambda 2 is 4. Lambda 1 is 2, lambda 2 is 4. Okay, so count from the 2 factors. Let me just write it. So lambda 1 is 2 here, lambda 2 is 4. So count from each factor. Okay, count from each factor. Okay. So let's find let's find eigenvalues, eigenvectors. Let's find its eigenvectors. Okay. Now find the eigenvectors correspond to lambda 1. Okay, let's find this matrix. So lambda SV equal lambda 1V. Lambda 1 is 2, so we want to solve this equation. Remember, S is 3, 1, 1, 3. XY. Suppose V is XY, is twice XY. So we get this is actually 2x, 2y. Write down this equation. Now on the left, the matrix multiply a vector. So what we get is write down. So the root times column. So we get a 3x plus y, x plus 3y equals 2x 2y. Wait, 2x 2y. So the first component gives us compare component. So this tells us 3x plus y equals 2x, or we get x plus 3y equals 2y. So either equation should give us the same relation. So for instance, the first equation gives us 3x minus 2x is negative y. So we get x is negative y. Now this gives us x equals 2y minus 3y, which is negative y. You see, what we get is the same relation. Okay, x equals negative y, x equals negative y. You can use either equation. You should get the same result. Okay, same result. Okay, so you see, then the eigenvector should be x, y. Now x is negative y. X is negative y. So this is negative y, y. So if you factor out the y, so it's a y multiple of negative y, y. Okay, so we choose okay, let's choose v1 to be negative y, y. But here, this is not unit vector. We find its norm. The norm is square root 1 squared plus negative 1 squared. So it's square root 2. So we divide a vector by its norm. So this is actually the unit vector. So we get a y over 2, this vector. Okay. Okay. So now let's do the projection matrix. Remember, S should be written as lambda 1 V1 transpose plus lambda 2 V2 times V2 transpose. Okay. So the projection on lambda 1 on V1. So the projection so we get lambda 1 V1 lambda 1 lambda 1 V1 times V1 transpose. So this will be lambda 1 is, remember, lambda 1 is 2. Lambda 1 is 2. V1 is 1 over root 2 negative 1 1. Now V1 transpose is column become root become column. Okay. Now this will be don't forget 1 over root 2. Sorry, 1 over root 2. So 1 over root 2 times 1 over root 2, we get 1 half. 1 half cancel 2. So this is actually 1 negative 1 1 times negative 1 1. Okay, you can either write root or column. Okay, you can write root or column. Okay, or you just root times column. So you get a you can just repeat it. Repeat the 2. So you get a negative 1 1. Then you get a 1 negative 1. Okay. You can also use matrix multiplication, or you use a root or column interpretation. Okay. Repeat a certain root or repeat a certain column. Okay, so this is the projection onto lambda V1 part. So the projection on lambda 2 on V2. So let's just do lambda 2. Remember, lambda 2 is 4. So we need to solve this. SV is lambda 2V, which is 4V. S is 3y13 xy equals 4xy. Suppose V is xy. Okay, so this will be 4x 4y. Okay, for x, for y. Okay. All right, so this gives us use matrix multiplication. So this gets 3x plus y, x plus 3y equals 4x, 4y. Okay, so component wise, what we get is component wise, we get 3x plus y equals 4x. X plus 3y equals 4y. Okay, so this equation gives us x, y equals 4x minus 3x. Move the terms 3x to the other side. So we get y equals x. Now this we get also x equals 4y minus 3y, which is y. Okay, so they are the same. X equals y, y equals x are the same. So we choose V to be the matrix x equals y. So we choose for x y y. But y is not unit vector. We divide by its norm. Its norm is root 2. Okay, so we choose V2 to be 1 over root 2 y. Now let's check what is lambda 2 V2 times V2 transpose. Lambda 2 is 4. Okay, V2 is this y. Now its transpose is y over 2 y. Okay, so what do we get is now root 2 times root 2, so we get 2. So we get a 1/2 times 4. 1/2 cancel a factor 2. So we get a 4 will becomes 2. So this will be 2 times y. Okay, y times y, you actually get y. Okay, you repeat the row twice or repeat the column twice. So okay, multiply by 2. So every entry just multiply by 2. So you get 2, 2, 2, 2. Okay, so this the projection onto V2 part. Okay, so remember S will be the projection, the two projections summed together. So remember, the first projection, the second projection we already have it is 2, 2, 2, 2. Now the first projection, if you forget, you just see it. We just see what we just. Okay, it's a y negative y. Okay, it's y negative y. Okay, add this together. What we see is now component-wise addition. So one entry, so we get 1 plus 2, which is 3. Now 1, 2 entry, we get negative 1 plus 2. Let's just write together. So it's negative 1 plus 2, negative 1 plus 2, negative 1 plus 2, 1 plus 2. So we get this is 3, negative 1 plus 2, y, negative 1 plus 2, y, 1 plus 2, 3. Okay, you see 3, 1, 1, 3 is exactly our original matrix S. Okay, this is S. Okay, if you check our S, the matrix S. Yeah, you see our matrix S is 3, 1, 1, 3. Okay, so this gives one example of spectral decomposition. Now this is only a trivial case. 2 by 2 is trivial. 2 by 2 is trivial. Okay, it's very trivial. Okay, homework for this section. Homework. Probably we will have a little more homework, and then we no longer have homework. Yeah. Recently some homework haven't finished grading yet, but I will try to finish grading soon. Okay. Okay, homework for section 6.4. Let's do number 8, then do number 13. Okay, let's do the next section, positive definite matrices. Let me start a new book. Okay. Okay, positive definite matrices. Positive definite matrices. Okay, we start with the definition. So, definition. An n by n symmetric matrix S is positive definite. Is said to be positive definite. Positive definite. If for all vector, for all non-zero vector X in Rn. Okay. We have X transpose S X is greater than 0, i.e. the inner product S with Sx is positive. Okay, is positive. Here we assume S is symmetric. Here we assume S is symmetric. In some different literature, you may see a definition that that without the symmetric condition. Okay, but here in this course, we assume in the definition that the matrix S should be symmetric. Okay. 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 And then S is called positive semi-definite if the strictly positive can be greater equal than 0. Okay, another definition. So S is said to be positive semi-definite. Positive semi-definite if still assume S is symmetric. S transpose X transpose S X. Now this is greater equal than 0. It can be 0. Okay. Now here we don't assume that X is 0. Okay, X is non-zero. Because if X is 0, then you just plug in. You get automatically it equals 0 for all X in Rn. For all X in Rn. Okay. Now this is a special kind of symmetric matrix. And then we give this definition, and then this kind of matrix should have nice property. Okay, of course we don't study ugly objects. Okay, now we study what kind of property this positive definite matrix has. First, positive definite matrix should have all positive eigenvalues. Okay, theorem. We assume it's a symmetric already. Okay, so without writing, then we just assume that S is symmetric. Okay, S is symmetric. Sorry, X is positive definite. Positive definite. If only if, all of if, and only if you see the IFF. This means if and only if. So it's equivalent. Okay, equivalent. If and only if all its eigenvalues are positive. Okay. 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 So it's easy to prove actually. It's easy to prove. So now one direction is trivial. One direction is trivial. Because if S is positive definite, then we know proof. If we assume that S is positive, then you see assume if S is positive definite, S is positive definite, then we have S, we take X to be eigenvalues with V with lambda an eigenvalue. And V an eigenvector corresponding to lambda. Okay, then we have S V dot product with V. Okay, dot product with V, or you use V transpose times the thing. So it's you do the dot product. Then you get this SV is lambda V. Okay, V dot lambda V. So this is actually lambda V dot product with V. Now this is the lambda V norm squared. Now we already, now by the definition, this should be positive. Okay, this should be positive for this inner product. This is positive. Now we know lambda V squared is positive. So this tells us that lambda should also be positive. Okay, positive. We know lambda is real already. Okay, lambda is real because it's symmetric. Eigenvalue of a symmetric matrix is real. Okay, so this tells us that its eigenvalue is positive because its eigenvalue is arbitrary eigenvalue. We know all eigenvalue of S should be positive. Okay, so this is one direction. Now another direction. How do we know the other direction? Now suppose all eigenvalues are positive. Now suppose all eigenvalues. Let me write down these steps. So since lambda is an arbitrary eigenvalue, then we know all eigenvalues should be positive. Then all eigenvalue of S, and all eigenvalues of S are positive. Okay. Okay, conversely, this direction. Now if lambda 1, lambda 2, lambda n, eigenvalues of S are all positive with corresponding with eigenvectors V1, V2, Vn. Okay, remember this V1, V2, Vn, they are orthogonal. Okay, they are orthogonal. So this spine, the whole Rn. Okay, so remember, since this V1, V2, Vn are orthogonal. So this spine, the everything, so the whole space. So this actually tells us that spine of them, V1, V2, Vn equals the whole space Rn. Okay, equals the whole space Rn. So any vector, then for any vector, i.e. V1, V2, Vn is actually a basis of Rn. So this is actually a basis for any vector for any vector x in Rn. We have a unique representation. X as unique representation of x by alpha 1 v1. Let's see, alpha 2 v2 plus alpha n vn. So where alpha 1, alpha 2, the alpha n are real numbers. Okay, they are real numbers. Okay, then we see X transpose. Okay, X transpose S X transpose. This will be what do we get? What we get is, now they are orthogonal. So this will be, if you write as so this will be alpha 1 v1 transpose plus the plus alpha n vn transpose times S alpha 1 v1 plus alpha n vn. Okay, now if you multiply S v1, we will get alpha 1 lambda v1 plus alpha n lambda n vn. Okay, remember they are orthogonal, pairwise orthogonal. Vi vj I orthogonal if I not equal to j. So you see, we only have, okay, so we only have the terms like this: alpha 1 squared, okay, alpha 1 times alpha 1, lambda 1, v1, okay, v1 norm. If we choose this eigenvector to be unit vectors, okay, plus alpha n squared, lambda n, vn transpose vn. So if by our choice, if we choose this as unit vectors, then what we get is alpha 1 squared lambda 1 plus alpha 2 squared lambda 2 plus alpha n squared lambda n. Okay, now a square is positive and the eigenvalues are positive. So every term here, every terms are positive. So their sum is also positive. So this is the positive because every term is positive. So every term above, every terms are positive. Then of course their sum is again positive. So we are done. Okay, so a matrix is positive definite if only if it's a symmetric and all eigenvalues are positive. Okay. Okay, next question is, now if I give you a matrix, how do you determine if it's a positive definite or not? Okay, now of course we have this eigenvalue criterion. Now find all its eigenvalues and see if it's a positive. All of eigenvalues are positive. The difficulty is, if we have a large matrix, then we need to solve the solve the characteristic polynomial. Find the zeros, find the root of certain characteristic polynomial. Okay, for lower degree, that's easy. Okay, for higher degree, in general we don't have, a formula by radical. So degree greater equal than 5, then we no longer have solution by radical. Then in that situation, find eigenvalues are difficult, not easy. Okay, not easy. So this criterion is not that good, perfect. Okay. Okay, let's see if we have other criteria. Okay, other criteria. Easier. So we have some easier way to determine if a matrix is positive definite or not. Okay, let's see this kind of examples. Okay. First, if we have a 2 by 2 matrix, how do we determine if it's positive definite or not? Okay, positive definite or not. So let's consider the case for a 2x2 matrix and see what we should do. Now suppose this matrix S is, so this, let's see, do an example. S is A, B, C, D. Okay, now let's see, we take any two-dimensional vector in R2 xy. Okay, now we find X transpose S X. This is, let's just compute and see what we get. Okay, XY, A, B, C, D, XY here. So we get XY, this we get AX plus BY, CX plus DY. Root times column, and then expand root times column, dot product. So this we get X times the AX plus BY plus Y times CX plus DY. Now if you rearrange this, try to rearrange this. Okay, so we get AX squared plus 2B XY plus CY squared. So this is actually a quadratic form. Okay, a quadratic form. Quadratic form. Okay, quadratic form plays an important role in mathematics. Okay, there are many books actually devoted to the study of quadratic forms. Okay, so this topic is actually really old. I think it's at the time of Gauss, actually people actually studied quadratic form, and it motivated many important thing in number theory, actually, quadratic form. So this actually quadratic form has a lot of interesting topic to talk about. Okay, now the only thing that we do today for this quadratic form is we want to determine when this thing is always positive for all non-zero xy. Okay, so we want to study this quadratic form fxy to be ax squared plus 2bxy plus cy squared. Now we want this thing to be positive for all for all pairs, for all pairs of xy which is not 0, 0. Okay, if you 0, 0 plug in, you actually get trivial 0. Okay. Now, well, let's see. Okay, so xy they are not simultaneously 0. Now suppose x is non-zero. Okay, suppose x is non-zero. Okay, let's first suppose y is non-zero. Okay, suppose y is non-zero. If y is non-zero, then you see we get, we can divide y squared, then this is ax squared, x plus y squared. This is 2b x over y plus c. Okay, this is a quadratic function in x over y. Okay, it's positive if only if it's always positive for all x. For the x over y can be any number. So this is always positive, tells us the quadratic function is always positive. Tells us so A controls the direction. It's U shape or the other manner. Okay. So this tells us A should be positive. Okay, A should be positive. And the discriminant be careful. Don't confuse yourself with determinant. Discriminant of a polynomial and is different from determinant of a matrix. They are different things. Discriminant is third is 2b squared b squared minus 4ac. 4ac. Okay, so you got this is the 4 times b squared minus 4ac. Sorry, ac. Third should be less than 0. Okay, there's no real solution. Does not intersect the x-axis. Okay, so this tells us this thing should be less than 0. Okay, so this tells us that b squared minus ac is less than 0. Or you write b squared less than ac. Okay, remember, so this actually tells us that c is c cannot be 0. Okay, c cannot be 0. Okay, c cannot be 0. Otherwise, 0 greater than b squared has no solution. Okay, so if you assume that x is non-zero, then what we just do is we flip a with c. So you get a c greater than 0. Okay, b squared, b is does not change. B squared less than ac switch ca. So we just still ac. Okay, so the condition that c greater than 0 is secretly already can be deduced from this condition. So we can only use this condition: a greater than 0, b squared less than ac. So this already tells us that c is greater than 0. Okay. Okay. If you write down c greater than 0, it's okay. So these two conditions already guarantee c is greater than 0. So 2 by 2 matrix ABCD is positive definite if only if this condition. Okay. So conclusion. Okay, so you may see it called a theorem. So ABCD, the 2 by 2 matrix, is positive definite. Is equivalent to a greater than 0, b squared less than ec. Okay. So we're done with 2 by 2 matrix. Okay. Okay. Now we started certain properties. Okay, certain properties about positive definite matrix. Let's see the property. Easier, we actually have this. If two positive definite matrix, then if two matrices are positive definite, then so is their sum. So this is actually easier theorem. If S and T are both positive definite. Now, of course, we assume S and T, they are the same dimension. Otherwise, it doesn't make sense. Then so is S plus T. Okay, it's very easy to prove. If we do dot product, inner product, X transpose S plus T times X. Now this is by the linear property. This is equals X transpose S X plus X transpose TX. Now each term is positive. This term is positive. This term is positive. So the sum is positive. Okay, for any non-zero vector. For any non-zero vector X. Okay, so this actually tells us that S plus T is positive, definite, by definition. Okay, this tells us that by definition, S plus T is positive definite, by definition. Positive definite, by definition. Okay. Okay, so the sum of two positive definite matrices is again positive definite. That's easy. Okay, the next one is a criterion that actually tells us when a matrix is actually positive definite. Okay. Theorem. Okay, suppose S, if we can write S as this form, A transpose times A. A transpose times A. Okay, A transpose times A. Okay. For a matrix, now be careful. We do not assume A is necessarily a square matrix. Okay, we do not assume that a matrix A is square matrix. For a matrix A, with the only thing that we assume for the matrix A is this matrix A has linearly independent column vectors. Okay, with linearly independent column vectors. Okay, then S is positive definite. Okay, positive definite. Okay, so for instance, so we do not assume that A is positive definite. So if we, we do not assume A is square matrix. Suppose if we write A as a matrix, let's see, M row n column. Now A transpose will be flip row with column. So it's a n row n m column. Okay, so AT times A, this will be, you know, we have this n times m, we have m times n. So their product, okay, m times m cancel out. So we have n times n, okay? So it's m n times n matrix. Okay. So if we want to show that for any non-zero x in Rn. Okay. So we want to find S x transpose. Okay. So the dot product with x, Sx dot product with x. So this will be xt. Now remember S is AT Now multiplication is associative. So you can write it as AT So this will be now transpose. Use the property of a transpose. So the AX transpose times EX. Now this actually AX transpose times EX tells us this dot product of the vector AX with itself. So this gives us the norm of AX. Okay, norm of AX. Now the question is why the norm of AX is non-zero. Okay, why the norm of we want the thing is non-zero. Okay, now we want the thing to be positive, so we need to show. So the norm is non-negative, but we need to make sure that the norm is not zero. Okay, we need to show the only thing that we need to show is that AX is non-zero vector for X a non-zero vector. Well, you see, you write. Remember, AS, let's use C1, C2. We know it's column vectors, they are linearly independent. So A is, remember what is A? A is M row n column, Cn. So column vectors.
So
now if you write x as
now the vector xy
xn, okay, in Rn. So x, the vector x is non-zero. So you see a times x, this will be x1 c1 plus x2 c2 plus xn cn. Okay, we want this is non-zero. Now you see, if this is zero, this is non-zero, because if it is zero, then we actually, by the linearly independent condition, that actually we get, because if x c1 x2 c2, do you think is zero? Because if this is zero, then we get x1 equals x2 equals xn. They are both zeros, okay? Because c1 and c2, the column vectors c1 c2 cn, they are linearly independent. I.e., if we have a linear relation that we get a zero, then the only possible case is the trivial case, i.e., all numbers, all scalar multiples should be zero. Okay, so they are linearly independent. So because x, the vector x, is non-zero, sum of the x1 x2 xn is non-zero, so we cannot, this linear combination is non-zero. Okay, this tells us that Ex is non-zero vector. Okay, is non-zero vector if x is non-zero. Okay, non-zero. Okay, this tells us then Ax norm for, you know, the norm of a non-zero vector is positive. Okay, the norm is zero if this vector is zero. Okay. Okay, so this actually tells us, this is actually what we want to show. Okay, so in this case, the norm of Ax is actually positive. So this actually shows that the matrix X is positive definite. Okay, so the matrix X is positive definite. So S equals ATA is positive definite by definition. Positive definite by definition. Okay. Okay. Let me summarize some conditions that we determine when a matrix is positive definite. Okay, here is a theorem. Some we already actually proved, some we don't. Okay, so theorem. For a symmetric matrix S, symmetric matrix X, S, the following are equivalent. Okay, let me short for the following are equivalent. So you may see this very often if you study pure math. Okay, the following are equivalent. Okay, so the following are equivalent. First, 1, all pivots of S are positive. Okay, 2, all in upper left determinant S are positive. We will give one example at the end, okay? Or n upper left determinant of S are positive. Now 3, all eigenvalues are positive. Remember, condition 3, all eigenvalues are positive. We showed that this is equivalent to S being positive definite, okay? So these conditions are equivalent conditions of a matrix to be positive definite, okay? For X transpose X greater equal than 0 for any non-zero vector X, okay? Now, number 4 is a definition of positive definite, okay? Number 5, we prove it, okay? Number 5, S equals A transpose A for a matrix A with linearly independent column vectors with linearly independent column vectors, okay? Okay, so we proved that we already done. We will not prove all of the cases. We already proved that 3 equivalent to 4. And we proved that 5 implies 4. 5 implies 4. And we even not prove that 4 equivalent. Okay. Yeah, actually we can find prove backwards direction of. How do we prove the backwards direction of 5? Now actually we can prove 4 implies 5. 4 implies 5. Now we may, already proved. Okay. Now we actually prove 4 implies 5 maybe next time. This time we don't have enough time to prove. Okay. Okay, let me mention about how do we prove 4 implies 5. 4 implies 5. Okay, 4 implies 5. So 4 implies 5. The idea. Okay, how do we prove 4 equals 5? Now from 4, we already know that this S is positive definite. Okay, positive definition. Now we already know 4 implies 3. Okay, all eigenvalues are positive. So, okay, we can write the diagonalization of S. Okay, so S we can write it as this form. S is D diagonal matrix P and P transpose. Okay, so S is congruent to a diagonal matrix. Okay, S is congruent to a diagonal matrix. Okay, diagonal matrix. All the diagonal entries of D, they are positive. Okay, diagonal matrix should be D equals diagonal matrix lambda 1 lambda n, where lambda I is positive, I equals 1 n. Okay. Then we can do it like this. So square root of D is well defined. How do we define square root of D? Well, square root of D is, well, we just square root lambda 1, square root lambda n. Okay, you check square root D times square root D is exactly this diagonal entry, diagonal lambda y squared, lambda n squared. Okay, this is a lambda y, lambda n diagonal. So so square root d is, we can define square root d. Then we can write in this form. Okay, so so if we write a as square root d times p, now at will be p transpose, now product of a transpose, or transpose of a product. We need to switch order, remember. Transpose, when we apply transpose to a product, to matrix product, we need to flip the order of multiplication. So P transpose, square root D transpose. Now square root D is again a diagonal matrix. So AT is PT times diagonal matrix D. Okay, diagonal matrix D. Okay, now D is, here the matrix D is full rank. D has full rank. Okay, D has a full rank. And because all the laminas, they are positive, non-zero. Okay, D is full rank, and P is also full rank. Okay, so they are both invertible. So A transpose A is actually invertible. A is invertible means it's non-singular. So A is actually with linear independent columns. So you check, then AT times A, this will be PT square root D times P. This is by associative law. Then this actually is PT D times P. This is exactly as. Okay, so we actually proved it. If we have a matrix, positive definite matrix, then we can write it as in certain form. Okay, A transpose times A for certain matrix A with linearly independent columns. Okay, column vectors. Okay, so we prove this proves, this shows, this proves 4 implies 5. Okay, 4 implies 5. So 5 and 4, they are actually equivalent. 4 implies 5. Okay. Okay, other conditions, actually 1, 2 is actually difficult to not, or tedious actually to show that. We will not bother to show that 1, 2 is equivalent to 3, 4, 5. Okay. Next time we will give certain examples that actually a positive definite matrix, of course, they satisfy all these 5 properties. And we will talk more examples next time about positive definite matrix and some applications of these positive definite matrices. Okay. Okay, we have 1 minute. Maybe let's just stop here for today because we don't have enough time for one example. Okay. Okay.